Okay, class, why don't we go over the exam and you can kind of get a feel, hopefully, for how you did here. All right, let's start with number one. And so I'll just write out the solutions here, but it says on a cold day of 6 degrees. Okay. Stationary outdoor open sound tubes produced sound waves. Now, a couple things. When they say open, that means open on both ends because one side always has to be open. So the phrase we use is either open or closed, referring to the end that has the option because the other option is always open. All right, so we have open and open. Okay, so both ends are open, and that's good to know here because it says produce sound waves at their fundamental frequency. All right. Now, the first thing that goes through my mind then is we've got a cold day, so the speed of sound's a little bit on the slow side, and these things are producing some sound waves. Okay, it says the left tube is a half a meter long and the right tube is 0.8. Okay, so if I go to calculate their frequency, I might say frequency 1 for the left and frequency 2 for the right. And this would be then the velocity divided by their wavelength. Maybe I better put wavelength 1 and wavelength 2. Okay. But the other thing that's going through my mind here is they said fundamental, and that would be then from an antinode to the next antinode, and that is a half wavelength. So we're really saying that the length of the tube is a half wavelength, or put another way, the wavelength is twice the length of the tube. So up here I could put V over 2L1, and here I can put V over 2L2. And so these would be the two different frequencies produced by the sound tube. Of course, I know their length, but let me also work on their speed. Maybe I'll go back here to the top and just say, so the equation for the speed was this 331 times the square root of 1 plus the temperature on the Celsius scale over 273. Okay, so I will take the 1 plus 6 over 273, and I'll take the square root of all of that and multiply it by 331, and I get a speed of about 334.6 meters per second. So that means right here, frequency number 1 would be 334.6 meters per second over 2 times a half a meter. And that's a 1, so that just comes out to be 334.6 hertz once the meters cancel off. So there's frequency number 1, and it's a smaller tube than this one, so I would expect it to be at a higher frequency. Let's run through this number for number 2. So this would be 334.6, and then I would divide it by 2 times point, let me check, 8 is the size of that tube. And so I guess I have it in my calculator already. 334.6 divided by, and that would be 1.6. And so that'd be 209.1. And that makes it fit really good. One of the things I hopefully emphasized was that smaller objects tend to produce higher frequencies than the bigger object. So sure enough, the bigger object has a lower frequency than the smaller object. Okay, so those are the two frequencies. Now, the real difficult part of this problem, I think, is right here. It says a sound detector is in between the two sound tubes and is moving either left or right. So it's moving towards the small one or towards the big one. The sound detector measures the same frequency from each. Okay, so there's motion and sound, and I hope in your mind you're thinking Doppler effect. And in fact, we know that if you move towards an object, the frequency goes up, and away from it goes down. So that would tell me that a movement to the right would be necessary because this one is naturally lower. So we want to kind of perceive this one higher and at the same time perceive that one lower for this to work. If we move to the left, the higher one would just be perceived to be higher and the lower one lower, and they would never match. So it's got to be moving to the right. And so there would be the first answer is to the right. But you can't really answer which way till you know the frequencies and you recognize it's a Doppler shift. All right, so there's half the problem, if you will. It's moving to the right. Now, the other one then, okay, how fast is this detector moving? Okay, and so it's moving to the right. And so this is a Doppler effect. And that general equation was something that looked like this. You know, F prime is equal to the real frequency. And then there was a motion of the observer and then a motion of the source. Now, in this problem, we don't have a motion of a source, so the detector is the observer, and the sound tubes are the source. And so they're not moving, but the observer is, okay? So if I'm talking about the smaller one, the one on the left here, its real frequency is 334.6. And the speed of sound, as we already said, is 334.6. And so let me also put a 334.6 downstairs. And then it would be moving with some speed. And as we decided, it must be moving then away, because it's moving to the right, so it must be moving away from the one on the left. And so away, let's see, would be the minus sign. And that's how we're going to get a lower frequency. Now, let me just split my paper here and say, okay, I can do the same thinking for the one on the right. The F prime would be the real frequency. This is the 209.1. And the speed of sound would be the same, 334.6, 334.6. But this time, instead of a minus, we'd do a plus because the detector, the observer, is moving towards the sound source. So the detector would pick up this frequency from the one on the right and this frequency from the one on the left. And the problem says it's moving at such a speed that they are the same. So I can just set these two equal to each other here. And so if I set these equal, in fact, maybe I'll simplify that math before I set it equal. I would have 334.6 minus V naught equals. And then over here, maybe I'll just do a little bit of algebra. There's the 209.1. And so if I divide it by the 334.6, I get a 0.625. 334.6 plus V naught. So when I do the distributive property, this 0.625 will go here, and if I bring that over, that gets 1.625 V naught. And then this over here would be this number times 334.6. So that's this side of the equation. And I'd move it over to this side, so I'd subtract it out. So this is 334.6 minus that last answer, and I get 125.46. So V naughts would be 77.2 meters per second. All right, so there's the two parts of the problem. Knowing it's got to go to the right, and we know that because these are the frequencies, and we know that because it's at fundamental, so we know the wavelength, and then we know the temperature, so we know the speed. That's how we got the frequency. And then we want them to sound the same, so we set those frequencies equal to each other, and then got that speed. So hopefully that one went well for you. That's number one. Okay, let's look at number 2. Okay, so number 2 says what? It says oscillations of 600 hertz are setting a standing wave waves on a string that is clamped on both ends. We've got a hanging mass, so there's going to supply the tension. It's 10.2 kilograms, has a mass density of. Okay, the standing wave has then these 4 loops, and so shown in the picture here is 4. and has an amplitude of 2 millimeters. What is the length of the string? Okay, now I'm hoping you can kind of see this is what we call the fourth harmonic. But you can also see from across here each little hump's a half a wavelength, so this would be a total of 2 wavelengths. So L is equal to 2 wavelengths. And a wavelength would be its velocity divided by its frequency. And its frequency would be the square root of tension over its mass density, and the tension would be equal to the mass hanging from it, since we have to have a net force of equal to 0. And so that allows me to do this calculation here to get the wavelength. So the mass is 10.2 kilograms. I multiply that by 9.8. That's just a hair under 100. Divide that by 0.000, and watch the units here. Since I've got newtons in the numerator, I need kilograms in the bottom. So I'm going to take the mass, which is in grams, and divide it by 1,000 to get kilograms. So that's what's under the square root. Let me take these square roots. And then the frequency, which was, 600, so divided by 600. And so I get a wavelength of roughly 2/3 of a meter. And so that means the length of the string, when I double it, is about 1 1/3 of a meter. And so there's A. What's the length of the string? Okay, so B says write an equation for this. Now you could write 2 traveling waves and do the same kind of mathematics we did in class, but that's really not the intent. The intent is to kind of start with the result of the standing wave pattern. And that's what you're supposed to recognize. This was a lot like a homework problem. There was one where you're supposed to just recognize it was a standing wave and then use that equation that they already derived out into the book here. Okay. Now, we got the 2A because we said that this would be, of course, the amplitude from each of them combined together. And this one is implying that the amplitude, of the whole thing is the 2. So I'm not going to say 2 times 2. I'm just going to say this then is 2 millimeters. And you can leave it in millimeters if you want, or turn it to meters like I just did. Now the K is 2 pi over the wavelength. And as we said earlier, the wavelength is about 2/3. So if I go 2 and a pi and I divide it by 0.667, I get an angular wave number of 9.42. So I'll put that here, 9.42x. And then the cosine has the angular frequency, which is 2 pi times the real frequency. The real frequency being 600. 600 times 2 make 1,200 pi, which I guess I could just write as 1,200 pi, but I think I'll just put it into a full decimal and get 3,770 times t, and that would be the mathematical equation of that point. Let's see how the phrase goes. It says, write an equation for the displacement. In other words, where is the point on the string? There it is. As a function of position and time. So you could pick any point on the string at any moment in time. Tell me what you want, and I can then use this to calculate what its y value is, what its displacement value is. Okay, now the one that was supposed to be the easiest, I hope it was. I haven't got a chance to look at anybody's test quite yet. But this one says, and this is the 10-pointer here, that we have a 100-gram mass oscillates on a horizontal frictionless surface due to the effect of a single spring as shown in figure 1. So hopefully you remember all kinds of neat things about the spring. For example, the omega was the square root of k over m. The period, which is always 2 pi over omega, then comes out to be 2 pi over the square root of m over k. And there's some other things we could figure out, but it turns out that this is the one we really want. Because as I read question A here, it says, if two identical springs, identical to the spring in figure 1, are attached to a new mass as shown in the figure, under the same frictionless conditions, what value of the mass would result in the same period of oscillations of the 100 grams shown in figure 1. So keep this in mind. This is the equation from number 1. In fact, maybe I'll even put mass number 1 here. But the thing to either remember from 121 or from the homework we did or work it out is that when you have more than one spring, there is then the combination effect, and it depends how they're connected. And so when we did something like this in class, like figure 2, we said the effective spring constant would be equal to one spring where you just added the two together. And since they said they were two identical ones, there's no point in calling it K1 and K2. I'll just call it 2K2. So if the conditions are the same, the period then would be this 2 pi divided by the square root of mass number 2 over this effective k, which is the 2k. See, and then we want this period here, which maybe I'll call it period 2, but to be the same as this one up here, period 1. Okay, so let me set them equal to each other. So period 1 is this, 2 pi times the square root of m1 over k. And period 2, we're saying, is 2 pi times the square root of m2, and its effective k value is 2k. So clearly, 2 pi's cancel off, and for that matter, the square root of k cancels off in the denominator. And then if we square both sides, we can see that we have m1 equaling to m2 divided by 2, or put the 2 on the other side, then we've got 200 times this 100 grams, giving us the 200 grams. So there would be the mass for number 2. Twice as much mass. Kind of makes sense. And then B is kind of that same effectiveness. Let's call this period number 3. And it would be 2 pi over the square root of mass number 3 over the effective k value. Now, for figure 3, and this was the harder one, and again, we can either go back to Physics 121 or in our lecture here, but what's the effective k when you hook springs in this fashion? And we discovered that you would get there by adding the reciprocals. And since these are identical, this would just be a 1 over k plus 1 over k, which is 2 over k. And when you flip it, then the effective k value then becomes k over 2. So knowing that and putting it up here, this would be 2 pi over the square root of mass number 3 over this effective k, which would be k over 2. And so that would be the period of number 3. And of course, the question says we want period number 3 to be the same as back here of period number 1. So let me set it equal to 2 pi over the square root of mass number 1 over k. And see, again, the 2 pi's will cancel off, and even the 1 over the square root of k would cancel off. And then I got these square roots. But if I then square the square roots, I get m3, and then this is a 1 over 2, if you will, and then equals to m1, or m3 is equal to 1/2 of m1. And since m1 is 100, half of 100 is 50 grams. And so we would get the same period if that one was 50, and if the second one was 200. And the first one was 100. These would all have the same period. So they have different masses because they have different springs. They're at least, they're two different springs, but I mean, I don't mean they're different. I mean they're hooked up different. They're identical, but the way they're hooked up would require a different set of mass. All right, well, I hope you did well with that, and I will hopefully soon get a chance to look at them and begin to grade.